One. Um, Solving an absolute value equation. If you remember, if you look up above here, our steps were to number one, isolate, isolate the absolute value. So if there's a number out in front of it or a number behind it, you got to get rid of it. But once you isolate the absolute value, then it's time to split it up into the two separate equations. You drop the absolute values and you get a positive on one side, a negative on the other, and then it's just two linear equations after that. So for us over here on the warm-up, we need to get the 7x minus plus 4, sorry, by itself. We'll multiply both sides by 8. So that gives me 7x plus 4 on the inside still equals 24. And now I've isolated the absolute value. So now we go with the fork in the road. 7x plus 4 either equals positive 24 or 7x plus 4 equals negative 24. And then I solve these independently. I would subtract 4 from both sides in each case. And in one case, I get 20, which gives me 27ths. And then over here, I subtract 4 and I get negative 28. And when I divide through by 7, I get negative 4. And I carefully find the right answer, which is in roster notation. And I notice that it's answer choice D, as in D right answer. There it is. Okay, so that's a review, a little warm-up review. Now, speaking of review, today we're going to learn about direct variation and inverse variation. It says inverse variation, but it's also direct variation. Sometimes variation is called relation. Direct variation or direct relation. Let me write it like this, and then I don't want to put another slash there. They mean the same thing, relation and variation. You had this in Algebra 1. You didn't get out of Algebra 1 without learning this, so we're just bringing it up again, and today should be pretty easy, okay? So this is pretty important because there's a lot of things in science and in real life that follow these types of relations with each other, or variations. They have direct variation and inverse. Let's talk about direct variation. This is very intuitive. Someone actually this morning in third period said, hey, I just took the TSI test, and this was on it, but we hadn't covered it in class yet. But I figured it out because it was like, duh, it was common sense. All right. Direct variation is when you have two quantities and they're related to each other. That's why we call them direct relation as well as direct variation. They're related to each other. And if one of them gets bigger, the other one gets bigger, impacted by the first one. If one of them gets smaller, the other one also gets smaller. So they are directly related. If one gets bigger, the other gets bigger. If one gets smaller, the other gets smaller. Sometimes we denote that with two upward arrows. It could also be two downward arrows, but they're going in the same direction. They are directly related. Can anyone think of something in the real world where direct variation is applied? Some quantity gets bigger, and because it gets bigger, the other one gets bigger. Yes, Jesus? Mass and volume. Yeah, I mean, that would work, right? If something's mass increases, it's taking up more space. The volume of that space is also increasing. That's perfect. That's right out of science. That's Pivnert or whatever. The ideal gas law gives you a lot of way to relate variables. So mass and volume, that's perfect. Anything else that y'all can think of? There's tons. Don't think too hard. How about anyone here have a job? Earn money? You earn money, yeah. How much do you get? The same amount every week? The exact same amount? Oh, there you go. What did you say? The magic word was D. It depends on how much you work, okay? When you say the word depends, you're talking about variation there. Something depends on something else, and it's directly related, right? The more hours you work, the less pay you get? Is that how that works? No. The more hours you work, the more pay you get. So your paycheck depends upon your hours. The fewer hours you work, the less money you get. The more hours you work, the more money you get. That's direct variation, right? Okay, now we can represent that mathematically like this. Y equals K times X. K is called the constant of proportionality. K is called the constant of proportionality. It says that somewhere in here. No? Oh, there, constant of variation, constant of proportionality, either one. Constant of variation, constant of proportionality. This is being multiplied by X. We take our constant of variation and multiply by X. So in your example, whatever your hourly wage is, Lauren, that would be K. So if you get like $5 per hour, 5 times 1 is 5, 5 times 2 is 10, 5 times 3 is 15. Hopefully you get paid more than $5 per hour. But that would be K. That would be your constant of proportionality. All right. Now, there's the other type of variation, which is the opposite of it, which we call inverse variation. And as you can imagine, this one is if something gets bigger, the other thing gets smaller because of it. If one thing gets bigger, the other thing gets smaller because of it. Or vice versa. If one of them gets smaller, the other one gets bigger. Can y'all think of anything in the real world that would follow an inverse relation or an inverse variation? What about pressure and volume from science? As pressure increases, what happens to volume? It decreases, right? You're confining it in a tighter space. So pressure and volume are inversely related. Okay, you get that from the ideal gas law. So it works the other way around. If pressure loosens up, then the volume increases. Things expand. Okay, so pressure and volume. What about temperature and the clothes you wear outside? As the temperature increases, do you wear more clothes outside? In general, no, you wear less clothes, right? And as temperature decreases, you wear more clothes to stay warm, right? Okay, so that's another inverse variation. Pretty simple. We represent that in an equation by y equals k divided by x. K is still your constant proportionality or your constant variation, but now we're dividing. We're dividing by x. Okay, so just like multiplication and division are inverse operations of each other, when you have direct variation, you're multiplying. Inverse operation or inverse variation, inverse relation, you're dividing by x. Now, what we're going to do in this section here is pretty easy. We're going to determine if something, excuse me, is direct or inversely related. We're going to be given an initial condition. An initial condition is basically a value of x and y that satisfy the equation. Like if you tell me how many hours you worked and how much money you got, we could figure out your hourly wage, right? We could just divide, right? We could figure out what k is. That's what we're going to do. And once we figure out k from that initial condition, we're going to substitute it back into these equations so that we can then use it to predict something further down the line. Like if you work 20 hours a week and you want to know how much you're going to make if you work 35 hours a week, once we know your hourly wage, we can just plug in a 35 and figure out what your paycheck's going to be before taxes, essentially. All right? So it's going to be multi-step. We're going to find k, and then we're going to rewrite the equation with k in it, and then we're going to use that equation to predict something in the future. All right? All right, let's try it out. The first way that we can be given the information is in a table of values, which is called data or numerically. What we want to do in each of these problems is figure out, does the data table set represent direct or inverse? So we have to decide, or neither. It could be neither, right? An example of neither would be the more cups of coffee I drink every day, the more auto accidents there are in the world. Are those related? And then the fewer cups of coffee I drink every morning, the fewer automobile accidents we have in the world. Are those related? Or is it the inverse? The more cups of coffee I drink, the fewer auto accidents in the world. Those have nothing to do with each other, right? Absolutely, absolutely nothing to do. So sometimes they don't have a relation. Let's look at this one here. The table gives the total cost in dollars of various numbers of tickets to a school play. What is the cost of 12 tickets? Okay, well, you might think the cost depends on the number of tickets sold. Would you agree? Like if you're buying them, pretend you're purchasing them. Pretend it's our school play and you're purchasing the tickets. Your cost to buy those tickets depends upon how many tickets you buy, right? The more tickets you buy, the more it's going to cost or the less it's going to cost. Which one? The more it's going to cost. So you might think right away that this is what? Direct or inverse? Direct. More tickets, more money. Fewer tickets, less money. Yeah. Now, the way that we look at tables is this. The top row or the left column, sometimes they're vertical, is always your X. And then the bottom row or the right column is always your Y. All right. Now, it works out that the way that tables or columns work, tables of values work, or columns of values work, is that your X is always increasing. We write your X, your independent variable, in increasing order. Okay. But now we got to look at what the Y values are doing just to verify. 12, 28, 36. What are those doing? Those are also increasing. So this could be direct variation, right? We've already thought about it. The more you buy, the more it's going to cost. So let's see if we can come up with the equation. So here's what we're going to do. We're going to think it's direct variation. So I think it's direct variation. So I'm going to put dv there. And then I pull out the formula for direct variation, which is multiply. Y equals k times x. All right. Now, here's what I want to do for a word problem. I want to write it in terms of the new variables. I don't want to use x and y because x and y are generic. I want to make it meaningful for my problem. So y is the total cost, and x becomes t, the tickets sold or that we purchase. So y equals kx becomes c equals kt. They mean the same thing, okay? Now what I need to do is I need to know a value of t and c at any given time so that I can find k. In other words, I need an ordered pair. Do we have at least one ordered pair from the table? We actually have three ordered pairs, don't we? 3 comma 12, 7 comma 28, 9 comma 36. I can use any one of the three. If it doesn't matter which one we use, I already see Aslan's writing down 312. We're going to use it. So here's what I'm going to do. I want you to be able to tell me which one you're using. So I want you to say at 312 and put a colon. That tells me you're using the point 3 comma 12 to find k. It's communicating what you're doing. Now, 312 is probably one that everyone would choose because the numbers are smaller, right? Who wants to use the bigger numbers, right? I know. Let's use the smaller numbers. Now, what I do is I plug in carefully. So I get 12 equals k times 3, and then I solve for k, and I get k equals 4. All right? Now, notice I'm running out of room here, so I'm going to go to a new column. Get in the habit of using new columns. I'm going to say the word so now, or you can use the word therefore. Now I'm going to write the equation. Because k is 4, comma, therefore the equation, if I just plug it right back in here, I get c equals 4 times t. The cost is 4 times the number of tickets sold. Now you can verify the other two rows that we haven't talked about. If the tickets purchased is 7, what's 7 times 4? 28. It works. If the number of tickets purchased were 9, what's 9 times 4? 36. It works. Okay. But now I can use this to determine what the cost is if I want to do, in this case, 12 tickets. So here's what I want you to show me. Since you're plugging in a 12 now for t, go ahead and say at t equals 12. That tells me now that in that equation, you're plugging in a 12 for t. What's nice about the equation is there's only two unknowns. So if I'm given t, I can just plug it in and find c. If you're given c, I can solve for t easily. Okay. If I know one, I can find the other. But in this case, I'm given t equals 12. So I get c equals 4 times 12, which is 48. Okay. Now, because this is a word problem, we always want to include units on our final answer. Always. What are the units of 48 in this problem if it's the cost? Dollars. So you can either write the word dollars on the back end of it, or dollars is one of those strange units that always goes in the front. So 48 bucks. Now ask yourself one last thing before you walk away. Is that a reasonable number? If 9 tickets cost 36, would it make sense that 12 tickets cost more than 36? Yeah. Now notice in the context of this problem, what can we say about 4? What is 4 in the context of this problem? What does 4 represent? This is the cost per ticket. Very good. This is your rate. This is your rate. $4 per ticket. Just like if you got $5 per hour, okay, it would be 5. It's the cost per ticket. Okay, very good. Now that wasn't very difficult, was it? In fact, you probably didn't need to go through that whole rigmarole to figure it out. You could probably just say, oh, it's 4. You can probably tell from looking at it, it's $4 a ticket. 12 of them is going to cost 48 and be done. What we're trying to do is we're trying to establish a sequence of steps that we can use every single time when the answer is not so obvious. So what do? We pulled out the equation and we changed the variables to match. We picked an ordered pair and we plugged it in and found k. And when I plugged it in, I will just re-emphasize that I'm showing what I'm plugging in. So, and then we wrote the original equation with k in it, and then we plugged in, showing what we're plugging in, the given value, and we solve for what the other variable. Okay, pretty easy. All right, questions on letter A, 1A. 1B, let's go to 1B. The table below gives the time in hours needed to drive to a destination at various speeds in miles per hour. What's the time needed to get to a destination when driving at a speed of 48 miles per hour? All right, let's look at this first of all. It's row and column again, or there are two rows, and then we have columns of values. So the top row is X, the bottom row is Y. So X is going to be speed, Y is going to be time. As you can see right here, the X values increase. They always should increase. But what do you notice about the Y values? These are decreasing. So this could be what type of variation? Inverse variation, right? Let's go ahead and write the equation then for inverse, IV, inverse variation. Y is going to equal K divided by X. Okay, Y is K divided by X. Now let's plug in our new variables to make it make sense to us. Y is time, so you get time equals K over speed, S. Now, this is one of the rare times where time is the dependent variable. In your science class, or usually in math class too, time is the dependent variable. Everything depends on time. But in this case, the time it takes to get somewhere depends upon the speed that you're driving, right? If your speed is greater, the time to get there should be smaller, right? And if your speed is slower, the time to get there should be greater. So that does sound like an inverse operation. All right. So now that I have the equation in terms of my variables, I get to choose any one of those three sets of ordered pairs right there to find the value of k. I'm going to choose 2030. You could choose 1250 if you want because the numbers are smaller, but I'm using 1230 because they're both powers of 10. They're just easier for me to work with powers of 10. So it doesn't really matter. That's the whole point I'm trying to make. It doesn't matter which of those ordered pairs. We're just going to tell which one we're using. So at 2030, I get 30. I plug it in for t, and I get k over s, which is 20. And then what math would I do to solve for k here? What would I do to both sides? Multiply both sides by 20. And 30 times 20 is going to be 600. You could do that if you had a calculator, if you needed it. We're not going to use a calculator much until the last problem here today. You just type it in, 30 times 20, enter, and you get 600. All right? So I plug that 600 back into here, and I get t equals 600 over s. And now I have an equation that I can use to solve for either variable. If you give me a t, I can find s. If you give me an s, I can find t. It's not that hard. You're going to be given one of the two unknowns, okay? Now let's answer the question that it asks. How much time is needed when the average speed is 48 miles per hour? So is 48 miles per hour here a t value or an s value? S value. So I'm going to say at s equals 48, colon. You're telling me what you're plugging in. You're telling me what the variable is. So I plug it in, and I get t equals 600 over 48. Now you could go off to the side and do long division, right? We just did long division of polynomials. Or you can go to the calculator and type it in, but you'll get t is equal to 12.5. And that's going to be what units? What units do we have on time? Hours. Yeah. So driving at 12 miles per hour, it took 50 hours. Wow. Going a little faster, 15 miles per hour, it only takes 40 hours. Driving at 20 miles per hour, it took 30 miles per hour. And now driving 48 miles per hour, it only took 12 and a half hours. Are those reasonable numbers? Yeah, as your speed is increasing, your time is decreasing to get there. Okay? So there you go. We did one direct variation. We did one inverse variation. Notice the format is exactly the same, right? Yeah. You write the equation, you plug in the ordered pair and solve for k. You write the equation, and then you plug in your new value every time, every single time. And if your notation doesn't look like this, try to step up your game. Try and write the way I'm writing up here, because if you write left to right or your work is all over the place, you're not necessarily trying to be an honor student. You're just trying to get through the day. We want to strive. The communication is a very, very important piece of this, right? The process is part of the product. So we want to clearly communicate how we're doing things. All right. Now, these are the exciting problems because they're word problems. You get to decide if they're inverse or direct. You get to assign new variables and units to it, and you can put yourself into the problem like you're the one driving there. How long is it going to take? But there are problems that are much more boring and much more direct. Problems like example 2. So I'm going to come up here and say example 1. These are the exciting problems, and I'm going to put an exclamation point, and then these are the boring problems. Boring generally means easier, though, too, doesn't it? We'll see. 2a, given that y varies inversely with x and y is 3 when x is 4, what is y when x is 6? That's boring, right? First of all, look at this. It tells us that y varies inversely with x. We don't get to figure it out for ourselves anymore. Thanks a lot, stupid question. I was looking forward to determining that on my own. Okay? Now, instead of having 3 ordered pairs to choose from, we have 1 set of ordered pairs to choose from. This is again called your initial condition. It allows you to find the value of k. And then it says, what is y when x is 6? So that's our final answer there. That's the last thing we're going to do. All right, so the first thing we do is the same thing we did up above. We're going to pull out the inverse proportion or the inverse variation equation. We get y equals k divided by x. Now, we don't change the variables here. That's kind of sad. We're just using x and y. So we're going to use the ordered pair that they give us at the point 4, comma 3. Be careful. 3 is listed first and 4 is listed second, but we always list the x before the y. So at the point 4, comma 3, colon, we get 3 equals k over 4, and we multiply both sides by 4, and we get k equals 12. Now, when you're working your homework, you might get a question that just says, what is the constant of variation? We'd be done, right? The constant of variation is 12. But in this question, we're trying to go further and find a y value. So we plug it back in right here, and we get y equals 12 over x. And now we have the equation that we can use to find x if we know y, and we can find y if we know x. It doesn't really matter which one we know. It's easier if they give us x, because it's already solved for y. But if they give us y, it's not too hard to solve for x. All right, here they give us x. So we're going to say at x equals 6, colon, we plug in and we get y equals 12 over 6, which is what? 2, and we're done. Piece of cake. Nothing to it. Working in columns, start a new column, right? Start a new column. It's okay to start a new column, but get in the habit of working vertically again instead of horizontally. When we were doing the polynomial stuff, there was always not a lot of room, so sometimes our work was all over the place. We were synthetically dividing over here, long dividing over here, factoring over here. But we want to try and stay organized. All right, let's look at part B. Given that y varies directly, okay, so now it's direct variation. Y is 18 when x is 3. That's your initial condition. Find the value of x when y is 36. So it's almost identical, but now we're pulling out a different starting value. We have to start with y equals k times x, direct variation. At the point 3, comma 18, colon, we get 18 equals k times 3. We solve for k by dividing 2 by 3. 18 thirds is 6. Be careful. I think there's one on the homework where those numbers are flipped. You have 3 equals 18k. When you divide through by 18, you get 3/18ths, which is 1/6, and not 6. So make sure that you get it in the right spot. But now that we know k is 6, I'm going to say so. Plug it back in right here. We get y equals 6x. Yeah. And now we're ready to rock and roll, or roll and rock, whatever you want to say. So be careful now. This is a little bit different. It says, what is x when y is 36? So now I'm going to say at y equals 36. And when I plug in, I get 36 equals 6x. So now, instead of being given the x and just multiplying by 6 to find y, I know y, I got to solve for 6. How hard is it to solve for, I'm sorry, we got to solve for x. How hard is it to solve for x? Piece of cake, right? We just divide both sides by 6. What's 36 divided by 6? 6, yeah. The other thing that makes these problems boring is at the end, there's no units to worry about. Boring. Boring. Is that $6? Nope. Is it 6 miles per hour? Have no idea. It's boring. It's just numbers on a page. This is just practicing the process. That's all it is. The word problems are really where the rubber hits the road. That's where we learn all this so that we can solve meaningful problems in our jobs, in our lives, whatever, and we can predict. It's always fun to try and predict the future confidently with mathematics, or to interpolate something that's already happened that we weren't there to see. Okay. Any questions on the boring ones? All right, example 3 is the last example, and these I want to write, these are marginally more exciting, if you're interested in the level of exciting for these problems. They're not as exciting as the first ones, because the first ones, we had to figure out if it was inverse or direct. These are word problems again. Hey, we like word problems, but they're telling us if it's inverse or direct. All right, now, for these, we do have to do one thing that is not as obvious as the others, okay? We have to clearly, I would write this down, we have to clearly identify x and y, okay? Clearly identify x and y. It's easy up above in example 1 because we had a table of values, and the top row is always x and the bottom row is always y. That's supposed to be an ampersand, sorry. X and y, there we go. All right, so let's read. The time T in days that it takes a theater crew to set up a stage for a musical. Hey, that could be the play from up above. It varies inversely as the number of workers, with the number of workers W. If 30 workers set up the stage in 4 days, how many days is it going to take for 24 workers? This is a classic SAT question or a classic TSI question, right? It's just a rate equation. Now, it tells you that they vary inversely, but what's X and what's Y? Because they're giving us T and W. Is T Y or is T X? Well, it turns out that most of the time, like 99% of the time, and of course the ones you're going to see, the first variable that you're going to see is going to be Y. And the second one that follows the word director inversely, the second one is going to be X. So Y is going to be the first one, and then X is going to be the second one listed. It's going to be the one that follows the words inverse, inversely, or directly. Okay. So let's pull out our equation. It's inverse relation. It says that. So I get y equals k over x. Now, just like in example 1, though, I want to assign it the correct variables here. So which one is y? Is ty or is wy? T. So I get t equals k over w. And now, before you just jump in, just make sure. Does the time to set up the stage depend on the number of workers, or does the number of workers depend on the time to set up the stage? I could see it both ways, right? If you know that you only have an hour to set up the stage, you better get yourself 100 workers because we got a boogie, right? But that's not what this question is saying. This question is saying the number of workers is inversely related to, or the time is inversely related to the number of workers. So this would mean the more workers you have, the less time it takes, and the fewer workers you have, the more time it takes, right? Does that make sense? Okay, so we got it right. T is Y. The first one listed is Y. So now our initial condition is right here. So if you want to write, it's important here to know the ordered pair. The ordered pair is XY, which in this case is going to be W comma T. Okay, so I'm going to list the workers first. So we'll say at the point 30 comma 4, colon, not at 4 comma 30, but at 30 comma 4, we get 4 days equals K over 30 workers. And to solve for K, I multiply both sides by 30, so 4 times 30 is 120. Now, K is unitless. K has no units. In this case, actually, it does have units. It's a rate. It does have units. It's a rate. Okay? But we're going to treat it as a constant, okay? So we get T equals now, we plug it back in right here, and we get K, which is 120 over W. Now we're ready to solve, right? Ask me any question you want. Give me the workers that are coming, and I'll tell you how much time it takes to set it up. Tell me how much time we have to set it up, and I'll tell you how many workers we're going to need, right? I can work both ways. It says only 24 workers are available. So I'm going to say at W equals 24. They give me the W value is 24. I want to know the time it takes. We only got 24 people. How long is it going to take? This is the easier of the two because it's just a plug and chug. It's 120 over 24. It's already solved for time. All right, so what do I get here? 120 divided by 24, how many times does it go in? It goes in 5 times evenly. Again, you have your calculator if you need it. 120 divided by 24 equals 5. Now, what are the units here? Days. Yeah. So 120, remember I said it was unitless? It's actually it actually is a constant. It's in days per worker. Days per worker, right? 120 days per worker. But you don't need to know that. You just need to know what your final units are. All right, so does that make sense? That's the last thing you want to do. Does it make sense? If 30 workers take 4 days, does it make sense that 24 workers, which is fewer workers, takes 5 days? Yeah, it takes a whole extra day to set up because we don't have as many people, right? That makes sense. Is that direct or inverse? That's inverse, right? Yeah, that's inverse. All right, we're on the last one. Are you sad or happy or neutral? Neutral? What'd you say, Bryson? Tired. Okay, that wasn't an option, but I'll take it. It was a write-in candidate like Biden the other day in New Hampshire. The time t needed to complete a certain race varies inversely. Okay, so they're telling us again it's inversely as the runner's average speed, with the runner's average speed s. Okay, so let's see. Think about that for a minute. The faster he runs, what do we know about the time to finish? Bigger or smaller? Smaller, right? And the slower he runs, the bigger his time, right? That makes sense. That's inversely, yeah. If a runner with an average speed of 8.82 miles per hour completes the race in 2.97 hours, what's the average speed of a runner who completes the race in 3.5 hours? Okay, so first thing we do is we pull out the y equals k divided by x. That's your inverse variation, your IV. Now we think about what is x and what is y. The time needed is first listed, so that's probably y. And what follows the word inversely? The word s, okay? So S is going to be your X. So if I write it now, I get T equals K over S. Now I've made it meaningful for my units. Now they give us this initial condition right here. They tell us that at a speed of 8.82, sorry, so at 8.82, comma 2.97, and again, that's x comma y. X comma y is going to be s comma t. So make sure you're listing it in the right order. Colon. We plug in and we get the time, which is 2.97 hours, equals k over the speed, which was 8.82 miles per hour. Now, how do we solve for k here? We just got to clear out the denominator, right, by multiplying both sides by 8.82. Now, here's where the calculator is really beneficial. I don't want to go off to the side and do a triple multiplication. So I got my calculator right here. I'll just do it for everybody because this is not a difficult calculation. 2.97 times 8.82 is 26.1954. Okay, and that's your constant of variation. You don't need to put units on there. Technically, it does have units, but you don't need to worry about it. Now, interestingly enough, that number, if it were in miles, is just a 2 steps short of a full marathon. A full marathon is 26.2 miles. And this is like somebody ran the whole marathon. They just didn't take that last step across the finish line. That's kind of what it looks like. Okay. Let's go ahead and plug it in now. We'll say, so we plug that K back into here, and we get comma T equals 26.1954. What a good year that was. Divided by S. And now, you give me T, I'll find S, or you give me S, I'll find T. I could do either one. Which one did they give us? They said, what is the speed needed if he's going to complete the race in 3.5 hours? 3.5 hours is the time value, isn't it? So I'm going to say at T equals 3.5, colon. And I'm going to plug it in for T. So I get 3.5 equals 26.1954 all over S. Now, how do I solve for S if it's in the denominator? Well, you can do two things. You can multiply both sides by S. That's going to work. And it'll divide out here. And then you can divide both sides by 3.5. So let me show you a little trick here. It's a little math trick that you can get good at with a little experience. These two right here, they switch places. It's called the double switcheroonie. That's the formal name of it, the double switcheroonie. You can replace things on a diagonal with each other, okay, in a math equation, in proportion. So I get S equals 26.1954 all over 3.5. It's like multiplying both sides by S and then dividing both sides by 3.5, which you can still do it that way. But the double switcheroonie works great. Now, this is just a plug and chug problem, right? So I get 26.1954 divided by 3.5, big bucks, no whammies. And I get the speed needed is 7.4844. And what are the units of speed here? Miles per hour. So we can put MI divided by H, or because we're in America, we could stylize the units as MPH, can't we? Where the P stands for what? Per. Yeah, we like doing that. Miles per hour, MPH. Okay. Now that's pretty fast. Speaking of running and marathons, a long time ago, it was probably thought among the American populace and even the world that you can't run a mile in under 4 minutes. It was a barrier that no one would ever be able to break. No one can run a mile in under 4 minutes. It's impossible. And then Roger Bannister one day, guess what? He ran a mile in under 4 minutes. And they're like, oh, I guess humans can run a mile in under 4 minutes. And now everybody runs miles in under 4 minutes, right? Everybody now. Once they realize it can be done, now everybody's doing it, right? No, it's still very hard to do. I can't do it. Okay, I've never been able to do it, even back in my running days. Um, but now the barrier is not the 4 minute mile. The new barrier in running in the running world is the 2 hour marathon. Okay, speaking of marathons, 26.2 miles. The world record has been creeping down towards 2 hours over the years. It was 2 hours and 4 minutes, then 2 hours and 3 minutes. The current world record officially for an official marathon is 2 hours and 1 minute. They are so close to breaking the 2 hour mark for the marathon. Now, that's pretty fast. You know how fast that is? When I used to run my marathons, I was in the 4 hour mark. I was taking twice as long to finish my marathon as the eventual runner. And what's funny is I ran the San Antonio Marathon one time. This was funny. The San Antonio Marathon was an out and back. So you had a start and a finish at the same place. So you would run like this, and you get to the halfway point, and then you'd run straight back along the same road. Actually, you'd run straight back along the same road. And they had like a divider down the road. Okay, so if you were going out to the turnaround point, you'd run on the right hand side, and if you were coming back, you would run on the right hand side. I think the River Road Marathon is the same way. You run out River Road, turn around, come back River Road. But anyway, what's funny is when I was about right here, still going this way, the guy that won the marathon, he passed me on the same road going this way. And I was like, holy moly, I'm not even to the halfway point for me, and he's already past he's already almost back at the starting line, which is the finish line. And it's just amazing at how fast that guy was running. He was running so fast when he passed me, he messed my hair up. My hair just kind of blew in the wind that he created. And I was like, slow down, dude. There's children around here. No respect for speed. He was booking it. Now to run, he ran like 2 hours and 15 minutes, which is still really fast. You got to average like 5 minute miles. That's fast over a 26-mile span. Okay. I never broke 4 hours. That was my barrier. I wanted to break the 4 hour mark, and I never could break 4 hours. And then my knees blew out one day, and now I don't run anymore. I just eat. Yeah. So anyway, we're done with direct and inverse variation. Y'all have any questions? Good stuff. Okay, there's like 9 minutes left. If you want to work on your homework, it's due tomorrow. There's a quick turnaround on 9.1. It's due tomorrow. Somebody finished it in class last period as I was teaching. And I was like, how'd you do that? And she goes, I multitask. I'm like, okay. Yes. Tomorrow we start 9.2.